for the answer. Because you literally could look at it and you'd be like, all right, it's this. And I'm like, how do you even just look at it? It takes them like 3 seconds to solve things. So that's not fair.
All right, guys, so let's take a look at this 2A. So it's going to work the same way. It's just got different numbers, and obviously, that sounds about right. So if you put that right in the middle, and I want to know between 2,000 and 3,000, I want that area there. So it's just like that first problem in number 1. You want to find a z-score for both. Never subtract z-scores. Because unacceptable definition of a z-score on a test, but an okay one when discussing things, is a z-score tells you where you are. So if you subtract 2 z-scores, you are now somewhere else. Does that make sense? No? Okay. You just don't want to tell me. So if I change 3,000 to a z-score, what'd you guys get for that? Can't read this. 350. What is it, sir? 0.22. That sounds about right. It's like barely above there, right? And then if I make 2,000 into a z-score, negative 2.62. There you go, Jeff. I like it. And again, you can kind of predict this. 2,000 is 900 below that. Every standard deviation is about 350. So 2 to 3 steps away, 2.62 makes sense. Okay, maybe. So now if I look these two up, when you look up 0.22, what do you get for the area? 0.587. Yeah. And then negative 262, looks like you get 0044. So then you get the area between, I just have to subtract those two. I like it. I like it. So about 58% of the 3-bedroom apartments in San Diego cost between those two. What about this guy? It's going to be just like this guy, just got a different value. So I try to get as close as I can to 15%. I know it's going to be where? Yeah, it's got to be down here, so it's only got 0.15 in it. And just to reiterate something I said last time, be really nice to yourself. This is true about any math class. Very often, students suck at algebra because they're not nice to themselves. They do the equation, they do some of it over there and some of it over there, and they try to bring it back together, and things go in the wrong place. So in this case, I always put areas up here. I always put raw scores and z-scores down here. 0.15 goes up there. I know I don't have the z-score yet. So I'm not going to do this that I see people do. 0.15. That doesn't make any sense. Because 0.15 is an area. It should be in here. And the z-score should be negative. So what's the closest you guys got? Looks to be a nice little history test. No? 1492. Columbus sailed the ocean blue. Killed all the Native Americans. Jackass. Sorry, I guess part Native American, so I don't relate. So negative 1.04. I like it. Negative 1.04. That's the z-score. So I know what that means. That means that the rent that is the answer is 1.04 standard deviations below the mean. And that it goes right along with what the formula wants me to do. It'd be the mean minus 1.04 of these. So if I start at the mean and I go down 1.04 of these, I'll end up at the answer. This would be like 2560 something there.
2556.78.
Yeah, don't forget that 78 cents. I like it. How you guys doing? You guys all right out there? I mean, these are exactly the kind of problems you're going to have to be able to do. On that quiz, for example. Yeah. Okay. This is almost the same question I asked up here, except now I'm asking for less than 1600, and it'll probably be about as unlikely. So if I do make this into a z-score, let's see, let's first do this. 1600 is way down here. What'd you guys get when you made this into a z-score? I don't think it's quite as drastic. 7.6. So it's the same situation, right? You look it up on the chart. It says I give up. It says 0.0001. There you go. I like it. Okay, so this, along with, remember, chapter 5 was uniform, the big rectangles. So we'll have some of those, and we'll have some of these kind of problems. I like it. So any questions from this handout before I leave it in the past? Okay. Now I'm going to do something that seems unrelated. And I don't seem to care. Oh, there we go. Perfect. Perfect. What I want you guys to do. I want you to figure out the mean and the standard deviation for this situation. So just to remind you guys. Those are the formulas you need to use. So just take a couple minutes and try to figure out the mean and the standard deviation for this situation. Ask her. I should just do that. Okay, I'll just. Now this real quick on the quiz, the first problem I gave you was this here, right? But I had a few people trying to use n times p and all that for the mean. One of the most basic things, you want to use the formulas that have x and p of x in them if that's what I give you. So how am I going to do what this guy needs? What do I have to do here? Yeah, I need to make a bunch of these before I can add them up. So if I just multiply across, no, get out. And if I add those up, that's the mean. And this should make, this should not be a surprise what you get. What do you guys get when you add these up? Yeah, why does it make sense? These are all equally likely. Bless you. These are all equally likely, right? So where should the mean be? Right in the middle. 2.5. Kick ass. It's only when the weights are off kilter and then you get a mean that's pulled one way or the other. What do I have to make this column? Yeah, and then the sum of those won't be a damn thing. It'll be a piece of the formula for that, for variance, or in this case, standard deviation. So if you multiply L1 times L3, or just this times this, you could do it, Jeff. Can you do it, Jeff? Is that 2.25? 4, okay. And then, what do you get there? 7.5? That is the sum of these. So that's going to go right here. And the mean was 2.5. And the most commonly forgotten thing is that poor little square dude. So let's see what you guys get. Get out of there. Yeah, what do you guys get? I like it. Now, real quick, just humor me, and you're like, that's all we do every day. If I were to take that and divide by the square root of 2, why? Just do that real quick. What do you guys get? 0.791. So make sure you get that. All right, so just keep this in the back burner. What does that have to do with anything? Nothing yet. Just want to do it right now because we got that right there. Later it's going to have a huge, huge importance to us. Now, do everything we just did for those. I was going to write those down, but I don't want to subject you to my handwriting if I don't have to. So take those values, do everything we just did. Calculate the mean, calculate the standard deviation. So if you wanted to do these in the calculator, you would put x in L1, p of x in L2. L3, I would make it L1 times L2. So that becomes x times p of x. And then L4, I'm going to let that be L1 times L3, because that'll become x squared p of x. Some of you guys squared L3 and did some other stuff. I don't want x squared p squared. So if I do L1 times L3, you can do it, Jeff. No, Jeff. There you go, man. Let me know if you need some help. If you do it in the calculator, the nice thing is you're not going to make a mistake putting all these numbers in the calculator. You're going to let the calculator do it all for you. So if I do sum of L3 and sum of L4, I've got those two parts. So that relates exactly to what we did earlier. Sum of L3 will be the sum of xp of x, which is the mean. So I know the mean for this problem is 2.5. And the sum of L4 is the sum of x squared p of x. So I know that's going to go in for that. And crazily enough, what do you guys get? Sounds familiar, maybe? Okay, so I like to do this. All right, this is the first time I've taught what we're about to get into this way. I like this idea of starting with the stuff we know from chapter 4. This is old stuff. We can do this. So now look at the reverse side of this thing that we were just working on. The one with all the two colors. Good job, Jeff. Oh, we got plenty of time. It's crazy. So here's the idea with this. If I put 4 numbers into a hat, they obviously, if I pick one out, they each have the same probability. 1 out of 4 chance of being picked. That would make a uniform distribution, right? Right, if they all have the same height? Are we all with it? That is if I pick one number at a time. That's what it would look like. I know the standard deviation is 1.118. We calculated that already. I know the mean is 2.5. That's if I do it several times. That's the average I expect to get. I like it. Okay. So what if I took 2 at a time? So instead of recording taking 1 and looking at it, I'm going to take 2, take their average, and then look at that. So instead of the results being just 1, 2, 3, 4, I could, for example, pick out 1, drop it back in, and I could pick out 1 again. So that would be down here. If I start taking every possible sample of size 2. And the reason we're doing this is, I don't know if you guys have noticed, you've had no reason to necessarily, but every normal curve problem we've done so far has been involving picking one thing, one person, one rent, one whatever. Right? Pick one thing. What's the probability it's greater than this? Pick one other thing. What's probably is in between these? But what do we almost always work with in statistics? The first thing we do in a lot of stats problems is we take a sample. So the problems we've been doing so far have been involving a picture that's created by looking at individual things. So then if I ask what's probably that this guy is greater than this, I could compare him to what everybody does and see what percentage of the people are out there and how likely is it. So when I take a sample of stuff, I can't compare that to individual things. I need to compare it to all the other possible samples to see where it falls. So this is kind of like the nuts and bolts behind what we're going to do. Thank God we're not going to do this exact thing ever again. Because I could do something very simple and say, what if I picked 3 out of the hat? 3 numbers and put them back in each time? Can you imagine how big that table would get? What could I get? 1, 1, 1, or 1, 1, 2, or 1, 1, 3, or 1, holy shit, I'm nowhere near done. You guys get that? Because that would be 1, 2, and then 1, 3, and then what about 2 something, and 3 something, and holy crap. So what we're doing is something we've done a lot in this class. We start with a very simple example, that you can actually do the way we're doing it. And then we try to see a pattern so that we can do larger problems without having to do all this specific stuff. Okay. So this table, that is every possible sample of size 2 I could pick. I could pick a 1 and then a 1, a 1 and then a 2. So what's the sample mean for this little tiny sample here? When you average those out, you get, what's 1 and 1? That was the average of 1 and 1. 1. It's crazy. I know. What's the average of 1 and 2? And remember, the average of two numbers is a number that's in the middle of them. Fill that out. Fill in all those yellow spaces. You should start to see a pattern to make this go quicker. All right, you guys with me? See the pattern? 1.5 is there, 2.5. So then this should be 2, 2.5, 3, 3.5. And you can double check. It is exactly what it's supposed to be. And then this one should start at 2.5, 3, 3.5, 4. So I really want you don't have to know where we're going with this right now, but just in this table, you guys all see that that's all the possible ways to pick 2 pieces of paper out of that hat, right? And then all we did, so instead of me writing down, for example, individual ages, if I were to take 2 people, average, write it down. 2 people, average, write it down. That would be my data now, would be the averages of every sample of size 2. That's all we're doing right here. So instead of the data being 1, 2, 3, 4, the data is now 1, 1.52, 2.53, 3.54. And of course, what's the least likely averages to get? What's the averages that happen the least? 1 and 4. They're the least likely to happen because they require you to get just one pair of things gets that. So why is 2.5 the most likely? Because there's a lot of different pairings that give you that. So that table just shows you the probabilities of getting each of these sample means. I like it. So, and all I did here was graph the histogram. Right? So the biggest thing is in the middle, is 25%, and then it goes down both ways. So notice something. Did this look normal at all? Hell no. It doesn't start low, go high, go low. But does this look normal, roughly? Yeah. Starts low, goes high, comes low. Yeah, it looks normal. So there's several things happening here. How big was the samples that I took? All the samples I took were how big? Each sample I took had how many pieces to it? 2. Right? I was taking 2 at a time. So my sample size is 2. Notice, now we did this. We calculated this. But do you see how the standard deviation for groups of 2 was the old standard deviation for individuals divided by the square root of 2. So what would you predict it would be if I took groups of 3? Yeah, it would be 1.118 divided by the square root of 3. And that is true. That is true. If we did it again and this big-ass table for picking 3, 1, 1, 1, 1, 1, 2, 1, holy shit, did all this work, it would end up being what it was when it was 1 at a time divided by the square root of n. That is almost too nice to believe. But again, we did one example. We could do another one, but it gets a little bit huge. So, let's see. Here's one little quick example. Give me, yeah, I like it. So if I knew that the standard deviation for individuals was 41.79, what would it be for groups of size 5?
208.95.
What?
I just multiplied by 5.
Don't multiply it, do what I just said. So how do I find the standard deviation for groups? In fact, think about this real quick. If I take one person at a time, could I get somebody who's really far away from the average? Yes. If I take groups of people at a time, is it really likely that I would get a group of 5 people who are all young? No. What's more likely, I'm going to get a mixture. So the spread of groups should be smaller. In fact, I'm going to do an example in a minute that involves what I used to use, alternate universe Florida. Maybe I'll use that statement. So this one would be 41.79 divided by the square root of 5, which is whatever that is. Who did it? 6.8, whatever, blah, blah, blah. Okay. So, here we go. Here's the last thing we'll do today. That gets everybody excited, but it's going to take a little while. Dadgummit. There you go. Okay. All right. So say I go to alternate universe Florida. Right? Why do I say that? Because I want the distribution of ages to be a certain thing. So let's go to alternate universe Florida, right? We're in the MCU. We can do whatever the hell we want to. So we got to. And I go around and I ask Floridians, how old are you? And then I put a dot for that person. Right? So I go around and say, how old are you? I'm 1. Okay. Pop. How old are you? I'm 97. Okay. Pop. So forth, so forth. So I do that with everybody in this alternate universe Florida. It's a large population of people in this alternate universe Florida. So I end up getting something that looks like this. So what does that really mean? It means there were younger people, there were older people, but there was absolutely nobody in here, for example, right? Let's just say it's this way. That roughly approximates Florida. So you got a lot of young people, and then you got the old people retiring down there. I like it. Okay, so let's say, where's the mean going to be for this? Young, average with old becomes middle. Right, roughly. You guys with me? A little bit? Now, does this look normally distributed? Hell no. So this is for samples of size 1. So I just talked to one person at a time, plotted them. If instead I go to alternate universe Florida and I talk to groups of 15 people at a time. So I get 15 people and I say, calculate your average age, and then they tell me that. And that's where I put the points. I really want you to stay with me. So far we've been dealing with pictures that were based on individuals. And that's why all the questions were, if you pick one, what's the probability? Because then we have the spread for individuals. If I have a question that's like, if I take 20 people, what's the probability that their age will be greater than, holy shit, I got to have the distribution of all groups of size 20, and then I could do the problem. I don't want to create that every time, right? Because the table gets huge. So I want some theoretical stuff based on patterns we see. So if I were to take 15 people at a time, what would be the most likely thing? Would it be very likely that I got all my 15 people right there? If I were randomly picking them? No. what's the most likely thing to happen if I just randomly pick 15 people from this alternate universe Florida? Am I going to get nothing but old people? No. Am I going to get nothing but young people? No. I'm probably going to get a mixture. I love it. So I'm going to get more than likely, not always. Is it impossible for this to happen? No. But what's the most likely thing to happen? A mixture, right? And this is exactly going back to the other name for mean. What's the other name for mean? Expected value. So if I take more than one thing, if I take several things, 15, I expect the average to be the actual average of the whole population. So if I redraw this, and I love it, I can almost get in your head, you're all like, what the shit are we doing? We're discussing the concept behind this, and I try to do some of the concrete stuff behind that, and eventually we're going to get to what you're going to have to worry about. We're not quite there yet, so don't worry yet. I take 15 people and I plot. So I say, you 15, calculate your average age. And they say, we're 80. Okay, 80. Plot. But most often I'm going to get this. So this is probably going to start to look like this. A little tiny bump there, and then a big old bump there, and a little tiny bump there. Do you guys see why it might look like that? The most likely thing is a mixture. So I'm going to get the actual mean happening the most. And then the next likely thing would be a bunch of people here and a bunch of people there that has little mounds there. Okay. All right. This is Jeff's educated guess because I did not actually go to alternate universe Florida. That would be nifty. I don't know what drug that is you take. But does this look more normal than that? I'm not saying does this look normal. Does it look more normal than this did? Hell yes. I like it. Also, whatever standard deviation this is, how does this standard deviation relate? Is it bigger or smaller? Which one has a smaller standard deviation? The first one or the second one? And again, remember, standard deviation tells you the average distance from the mean to all the data points.